You are seated by the window of a Boeing 737, cruising at 35,000 feet through dark storm clouds. The cabin shakes with turbulence. Then, without warning, a blinding white flash fills the windows, and a thunderclap shakes the airframe. Lightning has just struck the aircraft. Most passengers freeze in panic. The pilots barely react. By the end of this video, you will understand exactly why. Lightning is not a rare visitor in commercial aviation. According to the Federal Aviation Administration, the average airliner in the United States is struck by lightning once or twice every year. Expressed another way, that is about one lightning strike for every 1,000 flight hours. With the U.S. fleet logging roughly 30 million scheduled flights each year, these numbers add up quickly. Tens of thousands of strikes occur worldwide each year, making lightning a routine part of airline operations, not an outlier. This frequency might sound surprising, but it is built into the way airlines and manufacturers approach safety. For every 100 flights, on average, at least one will experience a lightning strike somewhere in the world. Pilots and engineers expect it. They plan for it. The aircraft themselves are designed with this exposure in mind, from the first sketch on a drafting table to the last bolt tightened before delivery. The routine nature of these encounters challenges the popular image of lightning as a freak accident. Instead, it is a normal, predictable event, one that happens so often that most passengers will never know it has occurred. For the people who design, fly, and maintain these machines, the numbers are not just statistics. They are the baseline for every decision about materials, electronics, and procedures. In aviation, lightning is an expected guest, not an unpredictable threat. Lightning rarely waits for chance. In nearly 90% of cases, it is the plane itself that triggers the strike. As a jet moves through a charged cloud, its metal skin and sharp edges, nose, wingtips, and tail amplify the surrounding electric field. This field enhancement turns the aircraft into a lightning rod. The local field at the tip of a wing or nose cone can double or even triple the ambient strength, reaching the threshold where air molecules break down and a bolt forms. The aircraft's presence does not just invite lightning, it completes the electrical circuit, often launching the initial streamer that connects with a charged region in the cloud. Once that connection forms, the numbers involved are staggering. Peak currents in a lightning strike can reach up to 200,000 amperes. That is more than 10,000 times the current needed to power a typical household oven. The temperature inside the lightning channel can soar to 30,000 degrees Celsius, hotter than the surface of the sun. These extremes are not theoretical. They have been measured in both laboratory tests and in-flight data, with NASA's research flights capturing the sharp rise and decay of current as it races across the airframe. A bolt may enter at the nose, surge along the fuselage, and exit at a tail or wingtip, following the path of least resistance. For an unprotected structure, this kind of energy would be catastrophic. The sheer magnitude of the electrical and thermal forces at work is exactly why every detail of modern airliner design anticipates not just the possibility of a strike, but its inevitability. Michael Faraday's work in 1836 laid the foundation for one of aviation's most effective defenses against lightning. In his experiment, Faraday showed that a hollow conductive enclosure can shield its interior from external electric fields. The principle is simple. When a current, even as powerful as a lightning bolt, strikes a closed metal shell, the charge flows along the outside surface. Inside, the electric field remains nearly zero. Modern airliners are built as flying Faraday cages. The aluminum or conductive composite skin creates a continuous conductive envelope around the cabin. When lightning attaches to the aircraft, the current travels across this exterior skin, finding the smoothest path from entry to exit, nose to tail, wingtip to wingtip, without penetrating the passenger space. This equipotential skin means that even as hundreds of thousands of amperes race across the fuselage, the voltage difference inside the cabin stays negligible. The result is this: passengers and sensitive electronics are shielded, not by luck, but by the deliberate application of Faraday's discovery. Look closely at the trailing edges of a commercial jet's wings or tail, and you'll notice a row of thin, black rods jutting out behind the control surfaces. These are static wicks. Each one is designed to bleed away static electricity that builds up as the aircraft moves through the air, providing a safe path for charge to leave the airplane gradually rather than in a sudden, uncontrolled burst. Maintenance manuals specify that static wicks must be securely attached to the ailerons, elevators, and rudder, with their tips extending beyond the metal skin. Their placement isn't random. Every major trailing edge gets at least one, and often several, to ensure that no part of the airframe becomes a bottleneck for electrical discharge. At the front of the aircraft, especially on the nose cone or radome, you'll find another tool, the lightning diverter strip. Unlike the rest of the fuselage, the radome is usually made from non-conductive material to let radar signals pass through. The diverter strip, often a zigzag or straight metallic band, acts as a controlled attachment point, channeling any lightning strike around sensitive electronics. Together, these features turn the aircraft's skin into a managed network for electrical flow, guiding lightning safely from entry to exit without interruption. Carbon fiber reinforced polymer, or CFRP, change the way aircraft are built. Unlike aluminum, CFRP does not conduct electricity well enough to safely carry a lightning strike across the surface. That posed a new challenge for engineers when designing jets like Boeing 787 and Airbus A350. To solve it, manufacturers embed a fine copper mesh or expanded copper foil into the outer layers of the composite skin. This creates a continuous conductive path just beneath the surface. When lightning strikes, the current flows through the copper mesh, not the carbon fibers themselves. The mesh is thin, often less than half a millimeter, and it is bonded with extreme care to ensure there are no gaps or weak spots. Every panel, joint, and fastener must maintain electrical continuity so the current can travel smoothly from entry to exit. Testing by both Boeing and Airbus has shown that with properly bonded mesh, a CFRP wing or fuselage can handle a strike of 200,000 amperes without structural damage or loss of protection. The result is a composite airframe that acts like a Faraday cage, channeling lightning safely around the cabin just as a metal one would. On December 8, 1963, Pan Am Flight 214, a Boeing 707, was struck by lightning while holding near Elkton, Maryland. The bolt ignited fuel vapors in the left wing tank, leading to an explosion that brought down the aircraft. All 81 people on board lost their lives. The investigation by the Civil Aeronautics Board and NTSB found that inadequate bonding and vent protection allowed the lightning's energy to ignite the fuel. In response, the FAA introduced new regulations requiring continuous conductive bonding of fuel tanks and shielding for vent lines. These rules, written into 14 CFR 25.951, set the foundation for the rigorous lightning protection standards that every airliner must meet today. Lightning protection is not just theory. It is proven in the lab and in daily airline operations. At specialized test facilities, engineers fire simulated lightning bolts, some reaching 200,000 amperes, directly into full-size aircraft panels. Sensors track every millisecond, confirming that the current stays outside, never breaching the cabin or damaging flight-critical systems. In the cockpit, pilots follow a standard checklist anytime a strike is suspected: maintain course, check instruments, and report the event. Maintenance teams step in next, performing a routine inspection within 24 hours. They examine static wicks, diverter strips, and entry or exit points for any signs of heat or pitting. Veteran pilots and supervisors know these steps by heart. For them, a lightning strike is just another item on the log, handled with the same methodical care as any other part of flight, and part of the ongoing emphasis on safety. On October 10, 2014, a United Airlines Boeing 787 departing from London Heathrow was struck by lightning. 3 of its 5 cockpit displays went dark in an instant, a high-voltage surge triggered by the strike. The crew declared an emergency and returned safely to Heathrow. Investigators found that the aircraft's lightning protection mesh had worked as intended, containing the surge and preventing deeper system failures. Boeing responded with a service bulletin to further reinforce the bonding scheme on the 787's forward fuselage, and the Federal Aviation Administration made these changes mandatory. Even in a worst-case scenario, the design held. The aircraft was inspected, repaired, and soon back in service. Right now, hundreds of jets cross storm fronts, each engineered to turn lightning at 30,000 degrees Celsius into a harmless flicker. As air travel grows, so does our faith in design tested by nature's extremes. The next time thunder rolls outside your window, know that science is already one step ahead. Thanks for flying along.